Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Epen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@epen.info. Dr. Masood Parvania, who is an associate professor and associate chair for research and advancement at the Department of Electrical and Computer Engineering at the University of Utah. His research interests are on the applications of mathematical optimization methods, calculus of variations, and scientific computing to the operation and planning of interdependent critical infrastructure, cyber-physical power and energy systems, and the modeling and integration of distributed renewable energy resources. Welcome, Masood.
Thank you for having me, Gil.
Sure, yeah. So I want to start with one of your papers, Hydrothermal Scheduling in the Continuous Time Framework, in which you say continuous time optimization models have successfully been used to capture the impact of ramping limitations in power systems. Before we get to the details of this paper, Masood, could you talk a little bit about the electrical grid and how it is set up and some of the characteristics of that in the US?
Yes, sure. So electrical grid, we use it every day. It powers our houses, powers our businesses, but maybe not so many people know how that works and what is the structure of that. So power grid, first of all, power grid is a very big infrastructure and is in a 2000 report by the National Academy of Engineering in the US. It was called the most complex machine ever built by the human in the 20th century. So they call it the most complex machine, and that's, of course, the credit goes to all the great engineers and the inventors of the electricity grid in the late 19th century and the early 20th century. But the reality is that this is really the best name for that. It's the most complex machine ever built, and it consists of large generating units that are usually in the remote area in order to access to land and access to water, and also we don't want to really pollute the cities. And then the power that is generated by these large generating units is transmitted to the consumption areas, which are mostly the cities, using a large transmission network. And then within the cities, there is a vast network of power distribution system that we see every day in every street, which then distribute the power to the cities. So that's really like when we talk about the power system, power grid, it consists of all things together, from the generation to transmission to distribution network, and at the end delivers power to the customers.
Okay, so it's a large grid that production units can plug into to supply electricity, and then equipment or other things that can take electricity out of it, there is no storage in it, right? Is there?
And yet, that's mostly the traditional and the history of power grid, that there has not been really a large scale, a large quantity available for storing energy. So there has been traditionally options such as pumped hydro energy storage, which is large scale, but then there are like so few of them built in the grid because it's just an expensive project to do, and also there are not so many natural places that can be used to develop those pumped hydro units, because what they require is two reservoirs. So one on a higher elevation, one in a lower elevation. So you could pump the water to the higher elevation to kind of save the energy in terms of the kinetic energy in the water, and then you release the water from that higher elevation reservoir, and then that would, along the way, that would generate power. So that has been one of the most the largest projects of energy storage that has been used, but that's really like a mechanical way of storing power. But now
so that's called pump storage. But do we have pump storage in the U.S. grid?
Yes, there are a few of them. There are a few of them operational, but as I said, that's really limited to the availability of location to build those kind of storages. But then there are battery, of course, technologies that has been around for a long time, but mostly at the customer level, customer electronics level, not necessarily on the grid level. But in the past few years, in the past maybe 2 decades, there has been advancement on the technology of the batteries, and now there are quite a number of large scale, or what is called utility scale energy storage, battery energy storage projects that are being built around the country and around the world.
Okay. So in this paper, you're looking at sort of a combination of hydropower and thermal production of electricity, right? And you're trying to sort of optimize the production windows for these two modalities.
That's right. So this is actually a traditional problem in the power grid. It's called hydrothermal coordination and hydrothermal scheduling, because traditionally we have had both sources of energy in the power grid. So we have had thermal units, and we have had large hydropower projects around the country and around the world that generate power. But what has been happening is that there are like different ways of doing that. There are different ways of scheduling and coordinating the power that is generated by the thermal and the power that is generated by the hydro units. What we have tried to do in this new paper, so first of all, the problem is not new, but the approach that we have taken to solve the problem is different and new. So a little bit going back to the history of that. So back in 2014 and 15, I started to working on a line of work on continuous time optimization, continuous time optimal control on power system operation, power generation scheduling. And the reason for that was that we realized that whatever we have today, which is mostly based on discrete time optimization, trying to schedule the operation of power grid, is not really like a good option when it comes to capturing the fast variations of the renewable generation that is being added to the system. So it has been doing fine for a long time, but now that we have more and more renewable generation integrated in the grid, what has happened is that they have fast ramping. They change, like their generation changed quite a bit, like over like a small duration of time, which we call ramping, fast ramping, and that is simply not something that is captured by the traditional discrete time control and optimization approaches that we have been using in the power grid. So the simplest idea was that why don't we just go to the like extreme cases? Yeah, of course we could also reduce those, like the sampling time and the duration of the time that we do discrete time optimization, but we went to extreme and we thought, okay, so why not we just don't do the continuous time continuous time optimization. So we took all these traditional power system operation and planning problems and tried to reformulate them using continuous time optimization. And then like a few papers came out of that, and few new theories came out of that, because that helped to also better utilize the flexibility of the generating unit and the flexibility of the faster resources that are coming to the power grid, just like energy storage systems.
Yeah, let me ask you. So you say here, results show how the flexibility of the hydropower can reduce the need for ramping by thermal units triggered by intermittent renewable power generation. I don't know a lot about this, Masood, but I would have thought hydropower is more base load production. That's not true.
That's been what is used in the traditionally, but actually that's one of the most controllable resources that we have in the power grid, and that is usually utilized for like a frequency control in some grids. Not necessarily base load, but is actually very fast response. So, but the way we have been utilizing it has been just like you said, for really like trying to utilize it mostly for the cases that is only really like a frequency regulation at the worst case. But now we are utilizing it. This paper tries to utilize the flexibility that is inherent in that hydropower generation to coordinate with the flexibility of the with the uncertainty and variability that is demanded to integrate the renewable energy resources. So
So renewable power generation, for example, solar, it takes off when there is sun. It cannot produce anything when there is no sun. So it's pretty straightforward. Whereas hydropower, so when you turn the turbine on, that's when it starts to produce. But can you flexibly turn it off?
yeah, usually like it's not turned. Yeah, it's not really something. Hydropower is really something that you don't necessarily turn off, because also its generation is
Yeah.
dependent on the use of the water, because these are usually large dams, right? And there is
Oh,
usually like a water flow and release of water that we need for the other application, for the water applications, right? So it's really
okay.
like
Okay.
the power generation application of the hydro and the dams is dependent on the amount of the release of water, right? So within that constraint of like how much water is scheduled to be released, that's what we can play with, right? So
I
we
see.
can
I see.
play with how much of that water we can utilize to generate power, and that is what the kind of the optimization and scheduling is coming to the picture.
I see. So I don't know if this is done already, but if you can predict power requirements, the variation power requirements, then you could have some sort of an automated system that releases the right amount of water, right?
Yes, that is like already available. That's not something that we are
Okay.
developing. That is something that is already available. There are really advanced technologies on that. So, but we have been mostly focusing on the power grid side, power generation application side of it.
Okay. Okay. So you say with your modeling, a reduction of 34% of the structural imbalance in the system is achieved by using continuous time model. So essentially, the continuous time model or your approach, if it is implemented in that fashion, it reduces the structural imbalances, meaning the demand and supply requirements on the. on the grid?
That's one imbalance that exists, and the other imbalance that exists is that in power grid operation, so we usually have a day ahead operation that we try to schedule all these resources to be operated in the real time, right? So then there is a real time operation that we take the day ahead schedule and try to adjust it based on the most recent information of the demand that we have and renewable energy that we have in the system. So that is what the structural imbalance what is called there. So when we are utilizing like a discrete time optimization in order to schedule all these resources for tomorrow, we are with discrete time optimization. There's so much approximation involved in that day ahead operation that then when you go to real time operation, that adjustment is a lot. You have to do a lot of adjustment to catch up with the real time demand. But what we have shown in there is that when you do and apply the continuous time optimization in the day ahead operation scheduling, you leave less adjustment for real time operation. So that's what is that structural imbalance that is called.
I see. Okay. Let me jump into another paper entitled Preparatory Operation of Automated Distribution Systems, ADS, for Resilience Enhancement of Critical Loads. So you say for preparatory operation of distributed resources for enhancing the resilience of power delivery to critical loads against extreme weather events, adopting hurricanes as a use case, a high precision spatio-temporal hurricane impact analysis model is first developed to enhance the situation awareness of automated distribution systems and generate a set of hurricane-induced outage scenarios. So in some sense, you're preparing the grid to expect some sort of an outage pattern?
That's right. So this is another line of research that we've been pursuing in my lab, which relates to the increasing challenge that the power utilities have regarding the impact of large scale extreme weather events on the power grid. So you hear like in the news that there is a lot of large scale events happening all over the country, which include the hurricane and include the like a windstorm that we had like a few weeks ago in Utah. So nobody knew that we are going to get that large of a windstorm in Utah, but the wind speed that we had in that windstorm was really like hurricane level wind speed, wind gust speed. So what happens is that when this large scale event happens, they affect the whole city, right, and the whole distribution grid, and it's not just one like outage, one failure, two failure that we used to have in the power grid that results in failure all over the grid that is much larger than the notion of and the practices that we have been utilizing, the reliability practices we have been utilizing in the power grid operation. So that is what there is this whole new science of resilience has been developed and people have been focusing on in the past few years, which is concerned about looking at all these large scale rare events that could happen on the power grid and that could impact the delivery of the power to the customers. So now we are looking at these large scale events. They are rare, but when they happen, they are very high consequence. So we want to see how the grid is resilient against them, which includes first being able to withstand some of these outages. So we want to see if the grid can be withstand, which means that it just don't fail when you are facing with these events. Then, if there are failures, how soon we can bring back the grid to normal operation, which is this concept of bouncing back to the normal operation. So then there are so this is the whole notion of a resilience. So in order to do that, we need resources. We need additional resources. It has really become clear that when there are outages, you can't just when there are for example, there's a windstorm, there's a hurricane, there a lot of these power lines break, and there is a lot of it's very messy. It takes a lot of time to just repair those and bring the grid back to normal operations. One approach for one approach against that, one approach to improve that is to utilize local resources. So rather than relying on a utility crew to come and fix the power line, there could be some local resources that could join force together to form something that is called a microgrid. So microgrids.
So the issue here is in a shock like a hurricane or something, when the outages happen, there might be a lot of interrelated issues across the entire grid, right? So that's one issue. You say here the proposed model prioritizes a service restoration of critical loads by integrating customer interruption cost function. Which takes into account customer type and outage cost, as well as interruption duration, making restoration decisions. And so when you have a number of different outages that's sort of interrelated, there is sort of a cost minimization question on the entire grid, right?
That's right. So what happens is that at the end of the day, whatever local resource you have, they are not going to be enough to serve the whole grid, right? So you have to decide and prioritize some of the loads. That's what we have done in that paper, is that we have tried to develop these models. We have developed these models that looks at the availability of resources that we have and how much generation how much energy that we have stored in energy storage, how much fuel we have reserved for distributed generation. Then look at the type of loads that we have around, and we are prioritizing the loads that have higher outage costs. So the different loads have different outage costs. So for example, an outage in a residential for a residential customer for a household is going to cost much less than the same outage for an hospital, right? So that's the way we have tried to approach this problem by looking at the outage cost, which is a socioeconomic information about the electricity customers, right? So then and trying to prioritize those customers, power recovery to customers that are going to have higher outage costs, which is naturally going to be more critical customers, right?
Yeah. And so essentially trying to optimize within a set of constraints on the entire grid by taking into account the customer's cost, customers' requirements, as well as sort of in some critical requirements, the duration is going to be quite important, right? Hospitals and things like that.
That's right. So we are looking at how we can recover those customers faster, but given, of course, the constraints that are available on the grid, constraints of the resources, and so on.
Okay. You have another paper here, Deliverable Energy Flexibility Scheduling for Active Distribution Networks. So you say this paper proposes a fundamental model for defining and optimizing distributed energy flexibility, as well as deliverable energy flexibility as the aggregate distributed flexibility that's available for offering to the day-ahead energy market. And so deliverable energy flexibility. So what do you mean by that?
Thank you for looking into that paper. So that's actually I very much like that idea. For many reasons. So what happens is that application is still on the distribution system, but the application is more on the normal operation, not necessarily when you have an outage on the grid, right? So you just consider a grid, a distribution network in an urban area that there are a lot of distributed energy resources on that, right? So you see people are installing solar, rooftop solars, or energy storage devices, or there are the resources are being installed in the substation level. So what happens is that these resources could not only be used for reducing the demand that we get from the transmission network, and also could not only be used to improve the voltage profile or other technical aspects of operating a distribution system, but also could be utilized to provide back the flexibility to the transmission network, to the bulk transmission network. Basically, if you can schedule these small scale distributed resources, that then what you can do, you can kind of shape whatever you get from the transmission network, which is very important because that's where most of the large scale renewable energy projects are. So you are kind of trying to shape demand to whatever availability of the power is from the transmission network, rather than just being a passive customer, right? So then, but the reality is that when you are doing that, these distributed resources are in the feeders in the distribution network. So what you generate in the feeder in a distribution network is not necessarily something that is seen in the transmission substation that is delivering power to you. And the reason for that is that there are so many lines and constraints and the voltage reduction and the power losses that are within the distribution network that would result in whatever you do. For example, you generate 100 kilowatts of power in a solar facility in a distribution network. The same 100, you may not get the same 100 kilowatt in the network that is connected, in the substation that is connected to the transmission network, right? So that is the concept of deliverable energy flexibility we are proposing here. So how much of that distributed flexibility that you have in the distribution network is available to the transmission system operator, to the independent system operator at the substation level? And that is something that is not, you can't just calculate linearly. It's not because the grid is not linear. So you have to develop a model in order to try to optimize what is delivered to the transmission network at the substation level.
So if I understand this correctly, so the local distribution networks is sort of operating independently from the substation and the transmission?
Yes, not necessarily totally independently, because of course they are electrically connected. But what happens is that there are, at least on the ownership level, yes, there is a distribution system operator. There's a power utility that usually owns the distribution network and operates the distribution network. And then there's a transmission network that may be operated with the same operator, with the same utility. But there might be other organization like an independent system operator where operates the transmission network. So there are usually, but that is only in the case when there is a market for electricity, like in California, in New York. So that transmission network operator is usually not the same as is not the same operator as the distribution network. You are right.
So in some sense, the ISO doesn't have really visibility into the local.
You are right. You are right. That is so that's the jurisdiction of the ISO that is only looking at the transmission network. But with the increasing level of the renewable generation and retiring of the thermal generation on the transmission network, they are looking to engage the distribution system operators and distribution network and the resources that are in distribution network in the operation of the bulk transmission network. And actually, they related to this. Just 2 weeks ago, FERC, Federal Energy Regulatory Commission, came up with this order 2222, which actually mandates and requires development of practices by the ISOs to integrate the distributed energy resources in the market operation, which is exactly what is done in this paper.
Okay. Yeah, I would imagine there are a lot of inefficiencies the way that they're operating today. So this is, if we can do it this way, it will substantially reduce those inefficiencies.
That's right.
That is the goal, right? Okay. I want to go into another paper, Masood. So scheduling and pricing of energy generation and storage in power systems. And you say this paper proposes a fundamental model for continuous time scheduling and marginal pricing of energy generation and storage in day-ahead power systems operation. We talked a little bit about pump storage at the grid level. There are increasingly batteries at the very local level. As electric cars become more prevalent, those are also storage mechanisms. And so, from an overall system perspective, a lot of things are changing from a storage.
That's right. So what's happening is that, as I said, so traditionally we have not had a large scale utility scale energy storage system on the grid, and if we have had them, they have not been prevalent, and they have been being operated by the same system operator, right? But as we integrate more of these energy storage technologies, from batteries to pumped hydro storage to compressed air energy storage, what happens is that the question that arises is that what we have been utilizing, the models that we have been utilizing to operate the grid, is really the models that are designed to schedule and operate thermal generation, right? Or like a thermal or hydro generation. But now, and the same for the way we have the practices and the models we have been using to price electricity in a system that has only involved generating units, right? But now we have all of these energy storage technology being integrated at larger scale and larger number in the power grid. So the question is that, first of all, are those models that we currently have, we currently utilize to operate the power grid, are those appropriate, and are those the best tools that could be utilized to operate the energy storage system? And also the theories of pricing electricity that we have, are they adequate for also pricing energy storage devices in the system? So that's what the motivation of this research. So what we did, this is in the line of the continuous optimization models that we've been developing. So we developed this fundamental model that looks at that tries to co-optimize the operation of the generating unit and the energy storage devices, and develops the theorem of a new theory for marginal pricing of electricity in the presence of energy storage devices. And we developed all these complex and fancy mathematical calculation models, formulas for calculating price of electricity in the presence of energy storage. And the results has been really kind of surprising, that we know for a fact that what energy storage does, it stores energy at some times, releases energy at some other times, right? So that's why I call energy storage is a temporal transition of power, right? That's what energy storage does. But then the results show to us that the energy storage also saves and makes a temporal relation in the price of electricity. So price of electricity at the time that the energy storage is price of energy storage is charging is going to be related to the price of electricity when energy storage is discharging. This is really interesting result, and I really personally liked it very much.
Yeah, so as storage becomes more common, whether it is at the grid level or it's at local level, generally speaking, both the scheduling and pricing of energy has to change quite dramatically, and so that is the issue. There is an optimization problem that cannot just use the status quo. Because it is now it has the ability to shift pricing on an as needed basis if you have
that's right. So what happens is that's what we expect from energy storage to do, store energy at the time that there is a prevalence of energy and shift it to the time to the peak times that we lack cheaper energy. So that's what this result showed, that there is also an impact on reducing the price of electricity that we already knew. But what this new results, which is for the first time presented, shows that the price of electricity at that time is also related to the time that energy storage is being charged. So basically, energy storage also saves some information about the price of electricity, not just electricity itself.
Right. Yeah, you have another problem here, which is sort of related. So electric bus charging optimization with transit network constraints. And so this is a situation that you have electrified public transportation, long-range battery electric buses coming online, and associated charging infrastructure inflict operational challenges to both power distribution and transit systems. So again, there is a spatio-temporal optimization when, how much to charge electric buses.
That's right. So this is a interesting problem, because what happened that relates to my research interest on interdependent critical infrastructure. So my main research is on the power grid, but what happens is that many of the infrastructure, if we think about that, rely on the power grid to operate, right? So one of those infrastructure include the water network. So water network is really relies on the power that it receives from the power network in order to operate pumps and operate pumping stations, and also like all the electrical equipment in the water treatment facilities. The other infrastructure is the transportation infrastructure, right? So transportation infrastructure has been traditionally operated totally separately, because the main source of fuel, the fuel was the gas, right? But now we are seeing a trend of electrification in the transportation infrastructure, from electric vehicles to electric buses. And electric buses, I don't mean those buses that work with the wire connected to that, right, that we have had for a long time, but battery electric buses that charge at different locations, and then utilize that battery in order to operate the bus. So but we think about that. So, and there are like so just 5 years from now, there's going to be many of them. Consider 5-10 years from now that there is going to be many of these battery electric buses in the transportation network, right? And what they are going to do is that they are going to need to charge, and these charges are either going to happen at by bus depots that they park overnight, or they are going to be en route, which there are all these overhead chargers or like other wireless ground charges that they are going to use to charge, right? And there are now a few of them available in Park City, Utah. That's where the motivation of our research was. So what they do, it makes a big difference where they charge, because now they are also a moving kind of a load for the power grid, that they could charge everywhere. They could charge here, they could charge there at different times, right? But the reality is that it makes a big difference for the grid where they charge and when they charge. So that's what we have tried to do here. We have tried to model both networks. The transit network, which runs on a schedule. We know there is a bus route that they drive on that route and at the specific times. But then there is a distribution network, power distribution network, that at some points is connected to that transit network, to the bus chargers, right? So what happens is that what we have done in that paper, we have tried to coordinate the charging of these buses with the constraints of the distribution network. So we have tried to, but still within all the constraints of the transit network. So we don't want to charge it too late that that it runs out of power in the
Right.
middle of the road, and we don't want to charge it too early, so that may not be the best time for the power grid operation, right? So we have tried to coordinate that charging of these
Right.
buses so that it doesn't affect the power grid operation negatively, but also become some sort of flexibility that is provided to the power grid.
And there is a sort of a combined problem also as these number of buses, electrified buses, increase. There's also a transportation problem that needs to be solved simultaneously, right? So congestion, weather, those types of things could also affect this optimum
That's right. That's
charging.
right. So that's what we have done in this paper. We are not only modeling the power network, which is the power distribution grid, but also we are modeling the transit network of the transportation network and how the buses are running in that. And that's actually a pretty complex optimization problem. But the formulation that we develop is pretty efficient. That could be solved in a very fast fashion. You are right. There is. So we are basically modeling both networks here.
Yeah, and another paper, you touched on this already. It's about demand response scheduling for water distribution systems. So it's not something that I never thought about. So energy intensive infrastructures, water distribution systems are promising candidates for providing demand response and frequency regulation services in power systems operation. So water distribution is really taking electricity for pumps and so on. But there could be things in there that you could optimize, such as when the pumps come on, where water tanks exist and how they interact, and hydraulic operating constraints and so on, right? So it's again a simultaneous.
That's right. You are right. So this, as
problem.
I just mentioned, so this is yet another network that is relying on the power network to operate, right? Which is the water network. So, and that's quite actually that's not this is not the first time that we are exploring the application of demand response for the water network. So it has been already utilized in many actually power utilities and water utilities as a source of demand response, because these pumps are really these are variable speed pumps. These are really large pumps with large generation, that even by some percentage of like a reduction in the load or shift in the load of that, some like a reasonable amount of demand response could be provided for the power grid. But what we have done in the paper, we haven't just considered one individual pump or one individual water treatment facility, but we have tried to co-optimize this operation of these two systems together, such that not only we are trying to maximize the impact of that demand response to the power grid, but also eliminating any negative impact that like changing the operation of that pump or water treatment could have on the delivery of the water, right? Because the main function of a water network is to deliver water to customers. And if and they would only do demand response, they would only try to help maybe the power utility or get paid for that if that doesn't hurt their main functionality, right? That's what we have done in this paper. We have tried to model both networks to make sure that we are scheduling that demand response in a way that is not going to hurt the operation of the water network, and is also going to be the most beneficial for the operation of the power network.
Okay. And I want to close with your cyber physical power system resilience testbed architecture and applications. So this is something that implements, tests, verifies, and evaluates cyber physical resilience solutions for power systems integrated with the communication infrastructure. So this is a way to sort of test scenarios and come up with ways to protect the potentially.
That's right. So
so
one challenge that the power grid research faces is that we do research in the academy and we develop tools, but the reality is that there is a long way from turning this research that we are doing into something that is utilized actually in the utility and in the industry, right? And the reason for that is that this is not validated in a real world situation. This is we usually run these develop these methods and tools and new software on test systems that are not necessarily representative of the actual grid. So in order to close that lab, in order that gap, and in order to ensure that we are going to kind of take this models we develop to the next level. We have developed this cyber physical power grid resilience test bed that what it does is that it models the operation of a real power network in a real-time fashion. So that's a big difference. So these are which is the main component of this test bed is a real-time digital simulators that simulates the operation of power grid in real time, and then integrate many physical components such as relays, such as real-time automatic controllers, and also all these methods that we may develop, all those control methods that we may develop, in order to see how are these models and how are going to work with the real-time simulated power system, and also with all these other relays and the physical components that are connected to this real-time simulator, in order to see if this is really kind of trying to emulate the operation of a real power network in a lab space, right? So which kind of would help us to see if these models and methods that are developed are going to work in a real world, so that this is just one more step in order to ensure that we are validating the methods and are not just leaving them on a paper or on a toy code that is not applicable in the real world.
Right. Yeah. So in conclusion, I want to ask you, if you consider sort of a 5-year horizon, do we have sufficient investments in the power grid, or we need to invest a lot more into it to really make it robust and reduce?
So that's a very good question.
So
first of all, we have gone a long way. So utilities around the country have done a lot in the past decade or so in order to enhance the resilience of the grid. That has included installing many automation equipment, installing more monitors on the grid so they can have a better situational awareness on what is happening on the grid and where is the failure, where is the outage. So these are the things that we really need to do: increase situational awareness and increase control on the grid in order to make it more resilient. In addition to that, we also need more hardening on the grid. So for example, at some locations, we know we may be better off to bury the power lines underground in order rather than just exposing them on the air so that they break or they fail or the tree falls on them. So there are many hardening approaches has been pursued by the power utilities, and also there's a lot of installing smart equipment. In addition to that, there has been a lot of project installing energy storage, installing solar generation, installing other sources of generation for enhancing the resilience. So a lot has done, but of course that's just a beginning of that. I believe this is an opportunity for the power utilities to look at their aging grid and see what they want to invest on that in order to first of all modernize it and then enhance the resilience along with enhancing efficiency. So I think.
So where do you where do we stand? Where does the U.S. grid
So I
stand,
think like
let's
a
say, in
US grid
comparison to
is
the EU?
pretty robust, is very well designed, but I don't have a lot of knowledge about like EU grid, but because the topology is different, the sources of resources, the sources of energy is
Yeah.
different, the methods of operation are different. But the reality around the world, not just US, is that the power grid is aging. Power grid is one of the oldest infrastructures we have had. So in the communication network, for example, so we have gone through like 2G, 3G, 4G, 4G LTE, and now 5G is being installed, right? And the pace of the
Right.
technology in the
Yeah.
and the change of technology in the communication infrastructure is much faster than, for example, on the power grid. But in the power grid, we still have equipment from 70s, 80s, if not older, right? So what happens is that they are still working, but every equipment has its own age, right? So they are aging. At the end of the day, they need to be substituted with the newer ones. They are being well maintained, but still there are going to be failures that are not going to be repairable, right? So what happens? There is an opportunity there. It is aging. Then there is an opportunity for modernizing. I think and then there is of course a budget limitation, right? So I think it's a nice problem
Right.
from my point of view. It's a nice optimization problem to solve. Just one more optimization to try to kind of
Right.
have a multi-year plan of substituting the age equipment, adding more modernized resources and modernized monitoring and control controllers to the grid, while while acknowledge that it cannot be done at once. So it is probably a multi-year project to kind of modernize the grid at different scale, and probably there is still going to be prioritization of different locations that are going to serve more critical loads. I think this is definitely a nice problem to solve, and we have like many experts in the industry, many great engineers in the industry who are doing great on to operating the grid and making sure that we are having a reliable power in our houses and businesses.
Excellent. Yeah, this has been great,
Likewise,
Masood.
this was
Thanks so
great,
much
and
for spending time with me. And
thanks for having me, and I enjoy talking with you. Thank you. Have a good
good
day.
luck with all this research.
Bye.
Thank you.